Chapter 1: The Nature of Electricity. Electricity is the most common form of energy. Electricity is used for various applications such as lighting, transportation, cooking, communications, production of various goods in factories, and much, much more. None of us know exactly what electricity is. The concept of electricity and its theories have been developed by observing its different behaviors. In order to understand the nature of electricity, we're going to start with a bit of history and static electricity. It was discovered centuries ago that certain types of material would mysteriously attract one another after being rubbed together. For example, after rubbing a piece of silk against a piece of glass, the silk and glass would tend to stick together. There was an attractive force that could be demonstrated even when the two materials were separated. Another example demonstrated this phenomenon. After rubbing a piece of wool against a piece of paraffin wax, the wool and wax would tend to stick together, and there was an attraction or an attractive force between the two of them. This phenomenon became even more interesting when it was discovered that identical materials, after having been rubbed together with their respective cloths, always repelled each other. It was also noted that when a piece of glass rubbed with silk was exposed to a piece of wax rubbed with wool, the two materials would attract one another. Furthermore, it was found that any material demonstrating properties of attraction or repulsion after being rubbed could be classed into one of two distinct categories: attracted to the glass and repelled by the wax, or repelled by the glass and attracted by the wax. It was either one or the other. There was no materials found that would be attracted to or repel both glass and wax, or that reached to one without reacting to the other. More attention was directed towards the piece of cloth that was used in the rubbing. It was discovered that after rubbing two pieces of glass with two pieces of silk cloth, not only did the glass pieces repel each other, but so did the cloths. The same phenomenon held for the pieces of wool used to rub the wax. Now, this was really strange to witness. After all, none of these objects were visibly altered by the rubbing, yet they definitely behaved differently than before they were rubbed. Whatever change took place to make these materials attract or repel one another was invisible. Some of the experimenters speculated that invisible fluids were being transferred from one object to the other during the process of rubbing, and that these fluids were able to effect the physical force over a distance. Charles Dufay was one of these early experimenters who demonstrated that there were definitely two different types of changes wrought by the rubbing of pairs of objects together. The fact that there was more than one type of change manifested in these materials was evident by the fact that there were two types of forces produced: attraction and repulsion. The hypothetical fluid transfer became known as charge. One pioneering researcher, Benjamin Franklin, came to the conclusion that there was only one fluid exchanged between the rubbed objects, and that two different charges were nothing more than either an excess or a deficiency of that one fluid. After experimenting with wax and wool, Franklin suggested that coarse wool removed some of this invisible fluid from the smooth wax, causing an excess of fluid on the wool and a deficiency of fluid on the wax. The resulting disparity in fluid content between the wool and wax would then cause an attractive force as the fluid tried to regain its former balance between the two materials. Postulating the existence of a single fluid that was either gained or lost through rubbing accounted best for this observed behavior, that all materials fell neatly into two categories when rubbed. Most importantly, that the two active materials rubbed against each other always fell into opposite categories, as evidenced by their invariably attracting to one another. In other words, there was never a time when two materials rubbed against each other both became positive or negative. Following Franklin's speculation of wool rubbing something off the wax, the type of charge that was associated with rubbed wax became known as negative, because it was supposed to have a deficiency of fluid, while the type of charge associated with rubbing wool became known as positive, because it was supposed to have excess fluid. Precise measurements of electrical charge were carried out by the French physicist Charles Coulomb in the 1780s, using a device called a torsion balance, measuring the force generated between two electrically charged objects. The result of Coulomb's work led to the development of a unit of electrical charge named in his honor, the Coulomb. If two point objects, hypothetical objects having no appreciable surface area, were equally charged to a measure of 1 coulomb and placed 1 meter apart, they would generate a force of about 9 billion newtons, approximately 2 billion pounds, either attracting or repelling, depending on the types of charge involved. Now, this quantity of force may seem fairly large, and that is because we're describing it in a macro sense. Once we drill down into the subatomic level, that force becomes smaller and smaller, and it can be dealt with a little bit easier. The operational definition of a coulomb as a unit of electrical charge in terms of force generated between 2 points was found to be equal to an excess or deficiency of about 6,250 with 15 zeros after it. I'm not sure if this is called a trillion, but you get the idea. It's a very large number of electrons. Or, stated in reverse terms, one electron has a charge of about 0. With 18 zeros, 16 coulombs, which means one electron equals about minus 1.602 times 10 to the minus 19 coulombs. Being that one electron is the smallest known carrier of an electric charge, this last figure of charge for the electron is defined as the elementary charge. It was discovered much later that this fluid was actually composed of extremely small bits of matter called electrons, so named in honor of the ancient Greek word for amber, which was another material exhibiting charged properties when rubbed with cloth. Experimentations has since revealed that all objects are composed of extremely small building blocks known as atoms, and these atoms are in turn composed of smaller components known as particles. The three fundamental particles comprising the most atoms are called protons, neutrons, and electrons. Whilst the majority of atoms having a combination of protons, neutrons, and electrons, not all atoms have neutrons. Collectively, protons and neutrons in the atom make up the nucleus, or the center core of the atom. Each electron has a negative charge of minus 1.602 times 10 to the minus 19 coulombs, and each proton in the nucleus has a positive charge of 1.602 times 10 to the minus 19 coulombs. Neutrons have no charge, just mass that's associated with it. Because the opposite charge, there is some attraction or attractive force between the nucleus and the orbiting electrons. Electrons have a relatively negligible mass compared to the mass of a nucleus. The mass of each proton and neutron is 1,840 times the mass of an electron. An atom becomes positively charged when it loses electrons, and similarly, an atom becomes negatively charged when it gains electrons. So let's again look at the mystery of the materials being rubbed together, a piece of silk against a piece of glass, using our atomic model. By rubbing the silk on the glass, electrons are transferred from the glass rod to the silk, causing the glass to be positively charged and the cloth to be negatively charged, which then causes the two to attract. And by rubbing the wool on the wax, the electrons are transferred from the wool to the wax, causing the wool, in this case, to be positively charged and the wax to be negatively charged, which then causes the two to attract. The atomic model also explains the phenomenon that identical materials, after having been rubbed with the respective cloths, always repel one from the other. The fact that when a piece of glass rubbed with silk was exposed to the wax rubbed with the wool, the two materials would then attract one another. As well as the fact that rubbing two pieces of glass with two pieces of silk, the two pieces of wax with the wool, not only the glass pieces and the wax pieces repel each other, but so did the cloths. Atoms may have loosely bonded electrons in their outermost orbits. These electrons require a very small amount of energy to detach themselves from their parent atoms. Hence, they are referred to as free electrons, which move randomly inside the substance and transfer from one atom to the other. Any piece of substance which, as a whole, contains an unequal number of electrons and protons is referred to as being electrically charged. When there is more numbers of electrons compared to protons, the substance is said to be negatively charged, and when there is more number of protons compared to electrons, the substance is said to be positively charged. The basic nature of electricity works like this. Whenever a negatively charged body is connected to a positively charged body by means of a conductor, the excess electrons of the negative body starts flowing towards the positive body to compensate the lack of electrons that is in the positive body. There are some materials which have plenty of free electrons at normal room temperature. Very well known examples of this type of material are, for example, silver, copper, aluminum, zinc, etc. The movement of these free electrons can easily be directed in a particular direction if the electrical potential difference is applied across a piece of these materials. Because there are plenty of free electrons, these materials have good electrical conductivity. These materials are referred to as conductors. The drift of electrons in a conductor in one direction is known as electric current. Actually, electrons flow from lower potential, negative, to higher potential, positive, but the general conventional direction of current has been considered as the highest potential point to the lower potential point. So the conventional direction of electric current has just the opposite of the direction to that of the flow of electrons. More of that in a couple of slides. In non-metallic materials such as glass, mica, slate, porcelain, the outermost orbit is completed and there is almost no chance of losing electrons from the outermost shell. Hence, there is hardly any free electrons present in this type of material. These materials cannot conduct electricity. In other words, electrical conductivity of these materials is very poor. Such materials are known as non-conductors or electrical insulators. The nature of electricity is to flow through a conductor while an electrical potential is applied across it, but not to flow through an insulator even though high electrical potential differences are applied across them. The definition of drift velocity can be understood by imagining the random motion of free electrons in a conductor. The free electrons in a conductor move with random velocities in random directions. When an electric field is applied across a conductor, the randomly moving electrons are subject to electrical forces along the direction of the field. Due to this field, the electrons do not give up their randomness of motion, but they will be starting to drift towards the higher potential. That means the electrons will drift towards higher potential along their random motions. Thus, every electron will have a net velocity towards the higher potential end of the conductor, and this net velocity is referred to as drift velocity of the electrons. The electric current, due to this drift movement of electrons inside an electrical stress conductor, is known as drift current. If the electrical field intensity is increased, the electrons are accelerated more rapidly towards the positive material after each collision. Consequently, the electrons gain more average drift velocity towards the positive potential. Let's define electric current then. Electric current is the rate of flow of electric charge through a conductor with respect to time. It is caused by the drift of free electrons through a conductor in a particular direction. The measuring unit of electric charge is the coulomb, and the unit of time is seconds. The measuring unit of electric current is coulombs per second, and this logical unit of current has a specific name, ampere, after the famous French scientist André-Marie Ampère. If a total of q coulombs pass through a conductor by time t, then the electric current is defined by I, which is equal to q divided by t, which is coulombs per second, also known as amperes. For a better understanding, let's give this an example. Suppose 100 coulombs of charge is transferred through a conductor in 50 seconds. What is the electric current? As the electric current is nothing but the rate of which charge is transferred per unit of time, it would be the ratio of the total charge transferred to the required time for that transfer. Hence, here, electric current I is equal to 100 coulombs divided by 50 seconds, which is equal to 2 amperes. So far, we've been talking about charges flowing past a point in a conductor. Really, we haven't defined direction, and we're about to change that right now. We're going to define what is the direction of electric current. The drift of electron flow is shown in the diagram here from left to right. In other words, electrons are drifting from left to right. The negative charge flow is also from left to right. Now, the adopted convention of current flow is from positive to negative, which is the opposite to the electron flow. So we say the current flow in this conductor is from positive to negative, or from right to left in this diagram, which, at the risk of repeating myself, the electron flow is the opposite direction. So you might consider current flow as the flow of positive ions or positive quantities, whereas electrons are negative, they're flowing in the other direction. However, convention states that current flows from positive to negative. This ends Chapter 1.